All right, let's dive right into this explainer. Today, we're decoding how higher ed takes these massive, abstract educational blueprints and turns them into actual, hands-on software development. Have you ever wondered how someone goes from just staring at a course syllabus to writing the literal code that powers our digital world? Well, that's exactly what we're tracing today. We're going to break down the core concepts that transform students into actual software architects.
But look, before we write a single line of code, it's absolutely crucial to grasp the philosophy behind the curriculum. The end goal here isn't just to memorize a specific coding language. I mean, let's face it, languages come and go, right? As this objective perfectly highlights, the real mission is building adaptable, lifelong learners, people who can tackle constantly evolving tech challenges. Really, it's all about learning how to learn.
So to get there, we're going to cover 5 main areas: the new tech blueprint, enter object-oriented programming, the pillars of Java OOP, multitasking and code reusability, and finally, building interactive user interfaces.
Starting with Section 1, the new tech blueprint. Under the latest NEP 2024 guidelines, you'll see this curriculum is so much more than just syntax. It's this carefully designed framework meant to forge well-rounded tech professionals. Look at how, right alongside technical proficiency in core languages, there's this massive emphasis on analytical problem-solving and strict professional practices. And this matters, right? Because writing elegant code doesn't mean a thing if you lack professional standards or if you can't even figure out what problem you're supposed to be solving in the first place.
Moving right along to Section 2, enter object-oriented programming. So, transitioning into the primary tool developers actually use to build digital architecture. Take a look at this intense first semester course load. Notice how Java OOP really stands out here. It's designated as a foundational discipline-specific course. Basically, it anchors the rest of the curriculum. Because if you don't understand how to organize data into objects, you're going to have a seriously hard time wrapping your head around things like AI or complex data structures later on. And when you're in the trenches working with Java, you absolutely need the right tools to keep your code organized. Think of keywords like this and super as these highly specific precision instruments in a developer's toolbox. The keyword this points right at the current object you're dealing with. Meanwhile, super lets you reach back and grab functionality from a parent class. These tiny little keywords, they save massive amounts of time and basically prevent a catastrophic structural collapse when you're organizing complex overlapping code. Which brings us to Section 3, the pillars of Java OOP. And this brilliantly illustrates one of the absolute most vital pillars of the language, polymorphism. It literally translates to many forms. It's an incredibly powerful concept where a single method name can perform entirely different tasks based entirely on the data it receives. It's kind of like telling a smart home system to turn on. If it's a light, it glows. If it's a radio, it plays music. It's the exact same command, but a completely different execution based on the object receiving it. Now, developers utilize this in 2 main ways. Looking at compile time overloading on the left, you use the exact same method name, but you change the parameters. Like, say, calling a method to calculate the area of a square by giving it 1 number, versus calculating a rectangle by feeding it 2. On the flip side, with runtime overriding on the right, a child class completely overrides its parent class's method using the exact same parameters. This built-in flexibility is exactly what makes Java so incredibly dynamic. But to make runtime polymorphism work, it relies heavily on what we call abstract classes. You can think of an abstract class as a mandatory template. So, for example, a blueprint for a generic shape might have an abstract method called number of sides of. Obviously, you can't just draw a generic shape, right? But if you create derived classes from it, like trapezoids, triangles, or hexagons, this abstract class forces those specific shapes to define exactly how many sides they have. It's a brilliant way to ensure consistency across your entire program. Now, how Java actually passes data between these structures is totally crucial. When you use call by value, the program just passes a copy of the data. That essentially protects the original variable from being accidentally changed or corrupted. But if you use call by reference, which in Java means you're passing objects, methods can directly modify the original object state. Choosing the right approach here is absolutely essential for keeping your application's memory and its data completely secure. Let's shift gears to Section 4, multitasking and code reusability. To see how all this builds up into much larger systems, we have to start with packages. Think of packages as perfectly labeled folders inside a massive filing cabinet. By grouping related classes together, like, say, a mathematical circle demo, packages prevent names from clashing.
Without them, if two developers accidentally named different functions calculate, the whole program would just get hopelessly confused. It would be a huge mess.
But beyond just organization, we need efficiency. By implementing multi-threading, we can literally force the computer to run concurrent timelines. Instead of patiently waiting for one task to finish before starting the next, a developer can elegantly wake up independent threads at, say, 1, 2, and 3-second intervals to perform unique tasks, like printing good morning, then hello, and then welcome, all running beautifully in parallel. Though, as you can probably guess, multitasking like that can lead to some unpredictable errors, and that is exactly why developers write custom exception handling protocols. This is basically building a safety net underneath your code. By using try, catch, and finally blocks, the code can gracefully intercept a fatal issue, like a user accidentally triggering a divide by zero error. It catches the problem safely before it takes down the entire application. And finally, Section 5. Building interactive user interfaces. This right here is the visual payoff, where all those back-end blueprints, abstract classes, and multi-threading tools finally come together. By leveraging the mouse motion listener interface, the code dynamically captures the exact X and Y coordinates of the user's cursor. Notice how the applet canvas, painted bright red here, is constantly recalculating and repainting the text on the screen in real time as the mouse moves. It's pretty cool to see. Similarly, tapping into the key listener interface allows the program to intercept physical keyboard events. Every single time a user strikes a key, the program catches that event and immediately echoes those exact keystrokes directly onto a bright green screen. It's a really perfect, simple example of software instantly responding to human input. But to make those interfaces actually look good, developers have to choose between different layout managers. Notice the stark difference between the simple, fluid alignment of a flow layout, which is fantastic for just popping combo boxes and lists right next to each other, against the rigid, directional grid of a border layout. That one locks components strictly into the north, south, east, west, or center of the screen. It's all about choosing the right structure for the job. And when you combine those visual applet controls with the multi-threading concepts we discussed earlier, you get these incredibly engaging, dynamic results. Take a look at this continuously scrolling digital banner in magenta and green. It's actually powered by a background thread that's constantly manipulating a string of text, pausing for just a fraction of a second, and then repainting the screen over and over again. So, we have traced the complete journey today, going from the grand, lifelong learning objectives of a computer science curriculum all the way down to the exact keystrokes, threads, and abstract classes that build modern software. You now understand the blueprint, and you've seen the tools in action. So I'll leave you with one final, exciting question. What will you build?